Hello, curious minds. Here's a fun one to start. Why did the atom break up with the molecule? Because it thought things were just too massive to handle. Today, we are diving into atomic mass, basically, what makes atoms weigh what they weigh. To keep everything fair and square in the atomic world, scientists use carbon-12 as the standard ruler. One atomic mass unit, or U, is defined as exactly 1/12 the mass of a neutral carbon-12 atom sitting still, not jittering around. Imagine slicing that carbon atom's weight into 12 equal parts. One of those parts is our atomic mass unit. In kilograms, one of these units is about 1.660539 times 10 to the power of negative 27 kilograms, tiny, but standardized worldwide. But here's a twist. The mass of an atom isn't just the simple sum of the protons and neutrons you find inside. Thanks to something called binding energy, which holds the nucleus together, the actual nuclear mass can be slightly less. That's like having a packed suitcase that somehow weighs less than all your items separately, because the way they're arranged saves you weight. Also, when we say atomic mass, we include the electrons buzzing around the nucleus, but nuclear mass counts only protons and neutrons. So scientists must carefully keep that in mind when measuring with precision, making sure not to mix those two masses up. This distinction helps us unlock the secrets of what holds matter together at the heart of atoms. Let's imagine you're looking at the core of an atom, a tiny, dense center called the nucleus. This nucleus is like a tightly knit family composed of protons and neutrons. We denote the number of protons by Z. Think of Z as the atom's unique ID card since the number of protons defines the element. Neutrons, counted as N, join this family as well, and together they give us the mass number A equal to Z plus N. So, if you add up all the protons and neutrons, you get A, the total nucleons making up the nucleus. Now, each proton has a mass of about 1.007-76 atomic mass units, and a neutron tips the scales just a bit heavier at 1.008665 atomic mass units. When combined, this gives us the nuclear mass, denoted as m sub n. Picture the atom's symbolic name as a fancy badge, superscript A, subscript Z, then the element's symbol X, like carbon-12 written as 12,6 carbon. You might wonder, with all those positively charged protons packed together, shouldn't they just push each other apart? That's where the strong nuclear force comes to the rescue. At a scale of 1 femtometer, that's 1 times 10 to the minus 15 meters, unimaginably small, these forces work like an ultra-strong glue, overcoming the electrostatic repulsion and holding the nucleus tight. It's like a crowd of friends huddled so close that their grip overcomes any desire to push away. Alright, time to clear up a common confusion. What's the difference between atomic mass and nuclear mass? Think of an atom as a tiny solar system with a nucleus at the center and electrons swirling around. Atomic mass includes the mass of everything, the nucleus plus those electrons. But nuclear mass focuses purely on the heavy hitters inside the nucleus, the protons and neutrons. Mathematically, the nuclear mass equals the atomic mass minus Z times m sub e, where m sub e is the mass of a single electron. And that electron mass is quite light, about 0.000548 atomic mass units each. So multiply that by the number of protons, Z, and subtract it from the atomic mass to get the nuclear mass. However, there's another subtlety. Because of binding energy, that mysterious energy that holds the nucleus together, the sum of individual masses doesn't perfectly match the actual mass of the nucleus. Thanks to Einstein's energy-mass equivalence, E equals delta m times c squared, a tiny difference in mass corresponds to a significant amount of binding energy. Scientists use this mass difference to calculate nuclear binding energy, which tells us how stable a nucleus is. Imagine if your paycheck had a tiny deduction that paid for your health insurance. You see the net amount, but the deduction is crucial. Similarly, the mass defect reveals the energy bill for holding the nucleus tight and explains why some nuclei stick together better than others. Let's zoom in even further, right into the nucleus to explore its size and density. The nucleus isn't a fixed-sized ball. Instead, its radius changes depending on its mass number, A. We model it using the formula R=R₀ times A⁻⁻⁴, where R₀ is about 1.2 times 10 to the minus 15 meters. That means the nuclear radius grows roughly proportional to the cube root of A. To visualize this, if you pile up more nucleons, the radius increases, but at a rate that's less than linear, like adding more marbles to a spherical pile where the radius grows slowly. Next up is nuclear density, defined as mass divided by volume. Using the volume formula for a skier, 4/3 pi times the radius cubed, we find that no matter how big the nucleus gets, its density stays nearly constant around 2.3 times 10 to the 17th kilograms per cubic meter. That's unbelievably dense. Imagine squeezing a mountain inside a sugar cube. This remarkable constancy means nucleons pack really tightly, showing that nuclear forces saturate and don't get weaker simply by adding more nucleons. This property is vital for stability and explains why nuclei maintain certain sizes despite increasing mass. It's like having a super dense crowd where everyone has their own little space but refuses to pack closer. Now that we understand the nucleus's makeup, let's sort out the different nuclear family categories, kind of like a school roster. First, isotopes are members who share the same number of protons, Z, but have different mass numbers, A. For example, hydrogen-1, hydrogen-2, and hydrogen-3 all have one proton but differ in total nucleons because of varying neutrons. They behave similarly chemically but have different masses and nuclear properties. Next up, isobars are nuclei with the same mass number A but different atomic numbers Z. Carbon-14 and nitrogen-14 are great examples. Same total nucleons but different proton counts, leading to distinct chemical elements. Then we have isotones, which share the same number of neutrons N. For instance, carbon-14 and nitrogen-15 both have 8 neutrons. Isn't that interesting? It's like families who look alike in one way but differ in others. These classifications help scientists understand nuclear reactions, decay behaviors, and stability patterns. If you picture this as a table, each entry shows the element's symbol, mass number, atomic number, and neutron count, helping to keep the relationships clear. Time for a quick calculation to tie it all together. Consider deuterium, a hydrogen isotope with 1 proton and 1 neutron, so Z=1 and N=1, and an atomic mass of about 2.014102 atomic mass units. Our goal is to find the mass defect and binding energy, which measure how tightly the nucleus is held together. First, the mass defect equals Z times proton mass plus N times neutron mass minus the atomic mass. Plugging numbers in, proton mass is roughly 1.007 U, neutron mass 1.008665 U, so adding those gives about 2.015941 U. Subtracting the atomic mass, 2.01410 U, we get a mass defect, delta M, of 0.001839 U. Here comes Einstein's magic. Binding energy equals delta M multiplied by 931.5 megaelectron volts per atomic mass unit. So 0.001839 times 931.5 gives about 1.712 megaelectron volts. This positive binding energy confirms the nucleus is stable. Imagine it like a tiny energy debt paid off to keep the nucleus intact. This calculation shows how mass difference turns into a measurable energy binding nucleons together, fundamental to nuclear physics and applications like nuclear reactors and medical imaging. To wrap it all up, one atomic mass unit equals 1/12 the mass of a carbon-12 atom, which is about 1.660539 times 10 to the minus 27 kilograms. The mass number A is the sum of protons Z and neutrons N. Remember, atomic mass includes electrons while nuclear mass excludes them by subtracting Z times the electron mass. Nuclear radius follows are equals R naught times A to the 1/3, with R naught approximately 1.2 times 10 to the minus 15 meters, and the nucleus maintains an incredibly high and near constant density. The mass defect, calculated as Z times proton mass plus N times neutron mass minus actual mass, helps determine the binding energy using the famous E equals delta M times 931.5 megaelectron volts per atomic mass unit. In this way, the atomic nucleus is a dense, tightly bound core where these tiny differences play big roles in nuclear stability. Finally, classification into isotopes, isobars, and isotones helps us understand how nuclei differ and relate across elements. Understanding these nuclear properties guides us through the fascinating world of atomic energy, nuclear medicine, and more. That is it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.